In this part of the lecture series, we'll look at some basic analysis of network traffic. So what are some of the pointers that we're looking for if we have had an intrusion on a network? So it might relate to ICMP activity, and that typically relates to a ping sweep of several hosts on the network. We might also look for DNS activity, where there's some request to a DNS server, which can typically show the start of an intrusion. We might look at the TCP flags, especially for the SYN flag, where the SYN flag identifies the start of any connection. We might also look at basic ARP activity. ARP activity is often the sign of a computer joining a network and then it trying to get out of the local network. And obviously we might look at some application protocol activity. So we might have large amounts of data that we must trawl through, so it's important that we try and find the starts of any event and then be able to trace the timeline from that. One of the most basic flags that we have is the SYN flag, and this is an example using Wireshark for the display filter, and we can define that when the flag is set to a 1, then we can actually see all the data packets relate to that. So if we have a look at Wireshark here, we have it loaded in there, and so let's actually pick the SYN flag equal to a 1. So with this we'll see all the SYN activities inside the data storage. So you can see here that there are quite a few data frames in here. So we have 100,000 data frames, and it's obviously searching through them for any SYN activity. The problem with just going with the SYN flag equal to 1 is that we will also get the currencies of when the acknowledgement flag is also set. So we can see here, we see a great deal of SYNAC activity, and if we want to filter for just SYN on its own, then we can search for the TCP flag equal to SYN and for the acknowledge flag to be a 0. So that gives us a more focused analysis where we can just search for the start of a connection. So you can see here there is a connection from this host to this one here as we see our SYN activity, and this seems to be a connection to an email port, so that the user in this case looks as if they're actually sending an email message. The activity here relates to SSH activity. So we can see here, this is the 2 email ports, and then we can see here a connection to the SSH port. There is now 2 more email messages, and we can see here the finger protocol being used, and so on. So these SYNs allow us to actually get some details on the basic connections that were actually made. We can follow a connection if we require, and this should actually filter for us. So the SYN flag equal to 1 and an acknowledgement equal to 0 is important for determining all the network connections that occurred. Another important focus might be on a certain protocol. So in this case we could filter for the port equal to 21, and that will show us any occurrences of the FTP protocol. So if we have a look back, we can see here that we've actually shown some sort of activity here for FTP, and you can see that the user was the anonymous user. Okay, so we can now filter for purely FTP traffic if we're interested in that. So we can filter for port 21. If we think there's been an intrusion on port 21, then we can actually list all the occurrences. So you can see in this case, this is the FTP server, and then this is the host that has been connecting to that server. And we should be able to see the protocol itself and any TCP packets. So these packets here show the actual FTP protocol working at the application layer, where these ones are standard TCP packets, typically to make a connection or to disconnect it. So we can see here now that we have all our occurrences of FTP. So in this case we have our SYN, and there's an ACK coming back, and then we can actually see the details of any of our FTP traffic details. So we can see here in this case someone is logging in to the system with a username, password, username anonymous, and with a password as given there. This traffic here is taken from a standard DARPA traffic set. Another important port is the UDP port 53, and with this we see DNS activity. So DNS activity is typically a sign that a user is asking the DNS server to resolve the name of a domain. So in this case it might be for the Microsoft.com domain, and we see a standard query. And then after it we get a DNS response where it will actually resolve the IP addresses of the servers. So we can see in this case this is the reply back from the google.com domain, and these are the IP addresses which could be used to resolve that domain. So UDP port 53 is often a good place to start to see the basic network trace. So we can see here this is an example of what the DNS reply returns, and defines a number of IP addresses. We can also search for certain hosts that we're interested in. So in this case we have searched for 68.37.75.158. So at any time we can actually define an IP address that we're interested in, and so we can say 66.7.248.153, and then it should filter through and give us any activity from that specific host. We can search from the communications between two hosts. In this case, if the IP address is equal to the one we searched for before, and if the IP address is equal to 10.0.1.207, then we can get it to list. So this allows us to actually focus in on the communications just between two machines. So we can see in this case we can actually see there is some email communication, email sending between the two nodes here. This is a standard type of trace for SMTP. So we look back at our trace and we can see here that we have filtered for this individual node, of which we can see FTP traffic, and we also see some SMTP traffic here. We can also look for certain MAC addresses on the network. So each data packet itself actually has the Ethernet details. So we can see here a source MAC address and a destination MAC address. So we can actually search for a specific MAC address if we require. So we can see that the source, the Ethernet.source is equal to 000C 4F A3 58 and then 60, and this should search for this specific MAC address. MAC addresses can often be spoofed, so they can't be taken as a completely credible source of identity of a machine. So the MAC address can be searched, so we can see in this case that the address that we're actually looking for is this one here. So this is identified probably as the MAC address of the gateway. Any communication that we have between our host and the internet, the MAC address will typically be of the source port of the router in which we connect to. The IP address will be for the destination, but the actual destination port, MAC address port, will be the MAC address of the router port which we use as a gateway. Also, data frames coming back in will have a source port equal to the MAC address of the gateway. So we go back, and unfortunately we haven't found anything there. I think we can look for the destination. If at any time we forget what the actual expression is for the filter, then we can bring up our filter expression and then find the protocol that we're interested in. So in this case we're interested in Ethernet, and it's eth.dst. Still doesn't seem to like that. There we go. Okay, so this shows another example using the source Ethernet address. We also see broadcasts on the network, and a broadcast typically happens when there is some Arp activity. And the Arp activity gives us a basic fingerprint of someone trying to possibly discover the network. So we can see here this looks a strange type of activity where this node is continually asking for nodes on the network. So this might be a trace of an intruder who is scanning the network for these hosts. So the Ethernet destination of all Fs gives us our broadcast traffic. So we take that and then we define some broadcast. can see here that we're starting to get some broadcast traffic, and the broadcast traffic might give us a pointer to some scanning activity of the network. So this type of activity might look strange, but actually there's a reason for this, in that 10.0.1.1 is actually the gateway for this network. And what's happening here is that when data packets come in or requests happen for these machines within inside this network, then the actual gateway is asking what the MAC address is of that actual host. Once it gets the request, the reply back, then it can update its ARP cache, so it does not need to re-request it for some time. So we can see here a re-request happens sometime later because the gateway has aged out the old ARP entry. So an ARP opcode can also give us identification of ARP activity. We can see here that we have the Arp Protocol. And basically how it works is that if this machine wants to get out of the network and communicate with this machine, then it must acquire the MAC address of the gateway to be able to communicate out. So it knows what the IP address is of the gateway. So in this case it's 1.1. So it sends out an Arp request inside its own domain to all these nodes, and they listen to it. The router will stop the Arp going over the device, and then the port which has that address will actually return back only to the host who asked it what its MAC address actually is. So the Arp that goes out is who has 1.1 tell 1.102. So the reply comes back only to the device who asked for it, and it updates its Arp cache. Once it has this address, it can then communicate with the gateway and actually send to an external node. Same thing can happen when a data packet comes in for a node which is on the network. The router looks at the IP address, checks in its Arp cache to see if it has the MAC address for that IP address. If it hasn't, it'll send out an Arp request to the network, and then hopefully it will actually resolve it. So Arp is a beautiful protocol which allows the internet to actually change at an instance. So we can see here, this is an example of an Arp request who has 1.1 tell 102. So we can see here that the source and the destination MAC addresses relate to the source MAC address of the host which is asking for it, and then we broadcast across the whole of the local network. And this is an Arp request. There are various details within there, and it gives the MAC address of the sender, IP address of the sender, and the target IP address for the request. A reply that comes back in will look something like this, where the node actually says that I'm at this MAC address here, and we can see the reply, Arp reply, that actually comes back. Another type of activity that might look suspicious or might show us some surveillance is related to ping activity or ICMP. This could be related to a trace route or a ping. So in this case we've searched for ICMP type. ICMP.type, and then we can actually see any activity related to that. So we can see a ping request here followed by a ping reply. So you can see that IP is is encapsulating the ICMP packet. So we're not using the TCP protocol here. With inside the protocol field of the IP packet, we have a type 1, which is ICMP. Same again, ICMP. And then with inside the protocol itself, we actually have a ping request. And then we have a ping reply. So this is an important thing to trace for, in that it could identify some form of port sweep, of host sweep. Okay, so there's our ping reply here coming back within ICMP. We can also search for high-level protocols, such as for FTP. We can do the same for most other application protocols. So we define if HTTP request.method is equal to get, and that will allow us to get any get requests for HTTP. So we can see examples here, and this is when the request method is not get. So in this case we can see post activity and notify for HTTP. And we can do the same for any protocol. So we could do the same for FTP type activity. So we can say for FTP request or FTP.response, and then we can actually search for that protocol. So FTP.request is one option, and we can define ftp.request.command is equal to user, and this will allow us to see whenever a user has actually logged in to an FTP server. And we can see in this case, with inside this network traffic, there is a great deal of user anonymous traffic logins. This can look suspicious in that an anonymous user is maybe trying to hide their tracks. So we can see here, these are all the requests. So we have IP, we have TCP, because FTP is built on TCP, and we can see the details here are that we use the user command, and then the argument in this case is anonymous. So these are continual anonymous logins. We can follow the TCP stream if we require from any of the events. We can see here that Wireshark is building up the basic search filter for us, and this will give us a timeline of when the user logged in with anonymous and until the end of the FTP connection. We can also do it for not user, and we can see all the other commands which have actually been used for FTP requests. So a useful tool for an investigator, and we can see here this is the example. So in this case the user has logged in with anonymous. This is a port negotiation with inside FTP. They have changed the working folder to mailing list. Then they have went into archive and then into music, and the list command is gives a list back of what's in that folder. Then the user has returned this file here and then actually quit. So each of these are the data packets associated with that. So the stream is important for actually showing the communications to the server and back again. So this shows the trace here. and we open up Capture 2 and get rid of the filter, and we have our activity here. So we might search for the initial SYN. So in this case we have the start of a connection here, and then we can follow the basic stream from there. And we can see here that the user logged in with anonymous with some password. Then there was some messages came back. There is a port negotiation here with an FTP, and then the user themselves have tried to change to one directory above. Then they have went into the bin directory and they have listed what's in there. They went back up and then quit. So this might look like malicious intent because an anonymous user is trying to go up to a higher level directory and into the bin folder. Okay, so we'll have a look at an example of an analysis, some of the analysis tools. So we can see here that we have 100,000 data frames in here, and it's obviously difficult to find any traces of activity from the actual the data frames themselves. Luckily we have some basic pointers. We can look at the basic summary of it to see how long the timeline is. So you can see in this case it's 1400 seconds. And then we can also look at the protocol hierarchy. So the protocol hierarchy will give us an idea of the basic protocols, IP, TCP, even the application layer protocols. So that will give us some idea of the activity within inside the network traffic. Often this can be used in some sort of anomaly detection system. So you can see here that virtually or all the frames were Ethernet, and then we've got mostly IP data packets, a few other ones. So we have some Arp in here too. But then within the IP packets we can see that 98% of them were TCP packets. There's a few routing packets there, and there are some ICMP packets. So you can see there was 46 that could be related to a ping or a trace route. Within TCP we can see there that most of the traffic was actually HTTP. There was some email, a little bit of SSH, some data, and a tiny little bit of telnet, along with some FTP traffic. So these are good pointers to actually see what type of activity was in there. We can see most of the UDP traffic was related to the local Windows network using the NetBIOS service. And then there was some loopback information there. So we can actually have a look to see what the endpoints were of the actual conversations. So we can see where the basic data has went from and to. Just takes a little minute to generate this, because it's obviously got to analyze each of the machines. The data here that we're using is from the DARPA traffic that was created around 2000 and can be used to basically train on and to identify threats with inside the traffic. So let's see if we can get our trace now. We can see here that we have one trace. These are the endpoints. So we can see here for Ethernet activity, those are the MAC addresses and the number of transmitted bytes from each. Slightly that this is the router port, and these are more likely to be the nodes on the network, especially for this one. But we can see here that these are the addresses and the amount of bytes transmitted. In this case, only the transmitted data has actually been listened to, and that's why there isn't any received data here. So we can see here this gives us a list of all the data that was actually sent and received. We see for our local network we actually have some local traffic which we have captured, and then for TCP we can look at the basic protocols that were actually causing that, and then what the actual host addresses were for those protocols. So that's a useful way for us to actually determine any of the activity. We can also look at the basic statistics for the graph of the data packets. Just takes a little minute to generate. And we can see here the activity across the basic timeline, and this will often give us ideas as to when possible threats occurred. Another useful tool that we can use to analyze the basic events on the network is with a flow graph. So in this case we'll actually see all the basic flows of data in a graphical way. So with this we can actually see when the SYNs actually happened, when there was a SYNAC, when there was a finish flag to the actual connection. It just takes a little minute to generate. And it's from these points that we can actually determine when a conversation actually started, and then we can trace on from there. So the data itself there might be a great deal of data, so it's important that we set up these filters to efficiently investigate occurrences, especially so that we can set up the security in the future to be able to stop any threats on our systems. So we'll actually just stop that, and we can see here that we can actually determine when the basic events happened. So we can see there this node sent an HTTP request to this node. There was then a SYN, went from this node to this one, and then so on. So this gives us a basic timeline of activity between certain hosts. So we can see here there's a lot of activity between port 80 here for these hosts. And we can look at other hosts too, especially for broadcast traffic and so on.